All right, so let's talk about um, some logic. Okay, so whether employing inductive or deductive reasoning, mathematics uses a lot of logic. Okay, um, and so consequently, for the next 5 lectures, we're going to be talking about logic. And by the time we finish our discussion of logic, we'll be done with the first unit of material and ready to take your first test on this material. But anyway, so logic, yeah, it's a huge part of mathematics. In fact, Bertrand Russell once wrote the following. He said, "Mathematics and logic, historically speaking, have been entirely distinct studies, but both have developed in modern times. Logic has become more mathematical, and mathematics has become more logical. The consequence is that it has now become wholly impossible to draw a line between the two. In fact, the two are one." Um, that's actually my favorite answer to the question, what is mathematics? My answer to the question is, well, math is logic. Which sort of just passes the buck onto logic. So then you could ask, well, what is logic, right? And we're about to explore a little bit of logic, but to give you some idea about what Bertrand Russell is getting at here, so he wrote this. I can't remember when he wrote Introduction to Mathematical Philosophy, but it was in the early 1900s. It was probably around 1920-ish. And that was actually sort of later in his life, I suppose. He started doing a lot of work in logic and math around the turn of the last century, so early 1900s. Anyway, so in mathematics, what had happened is that in the 1700s, there were a lot of discoveries that mathematicians had made inductively, right? They had employed their inductive reasoning, and they had made a lot of discoveries, especially in calculus, but they had never really proven those deductively, right? And so in the 1800s, the work of mathematicians was largely to clean up what mathematicians had done in the 1700s, right? And so in the 1800s, mathematics became a lot more logical. There was a lot more deduction involved in what was in mathematics, and so mathematics became more logical. And then by the time Bertrand Russell was writing this, mathematics had become very formal, very formal. Anyway, and then logic at the same time, prior to the time that Bertrand Russell was writing, logic was largely statements written in English, but there were a couple people, Russell, I can't remember his first name, but Boole, Boole. Who else? Cantor. There were a few kind of logicians who were interested in making logic more symbolic to sort of cut through the sort of unnecessary words, right? Boole in particular was interested in trying to come up with sort of like a logic calculator where you could put your statements into a machine and the machine would tell you whether or not your arguments were valid, right? Anyway, so this led to symbolic logic, which is what we're actually going to be talking about for the next 5 lectures. So logic became more mathematical. And so, yeah, the consequence is that now there's really, it's impossible to draw a line between the two. Math and logic, they're the same thing. Math is it's just logic puzzles, right? So anyway, so let's talk about some logic. What we're going to talk about in this lecture are statements, connectives, and quantifiers. And it's basically just going to be an introduction to a few things. In the next lecture, we'll talk about truth tables and how to determine whether an argument's valid and things like that. Okay, but let's talk about statements, connectives, and quantifiers. So a statement in logic is a declarative sentence that is either true or false. Okay, so here are some examples of statements. AIDS is a leading killer of women. Maybe that statement's true, maybe it's false, but it doesn't matter. It's a claim, right? They're making a claim. right? It's a declarative sentence, so they're making some claim. AIDS is a leading killer of women. If you eat less and exercise more, you will lose weight. Okay. In the last 10 years, we have reduced the amount of greenhouse gas in the atmosphere by 25%. And then Garth Brooks or Taylor Swift, that should be a capital S, has the highest earnings in the entertainment industry in 2015, or had the highest earnings in the entertainment industry in 2015. Again, maybe these statements are true, maybe they're false. It doesn't matter. They're still statements, right? They're making some claim. Now, here are some things that are not statements. Come here, right? You're not making a truth claim. You're not, right? That statement is neither true nor false, right? It's a command, right? Come here. When did dinosaurs become extinct? Again, not a statement. That's a question. Part G. This statement is false. Now, this one is a tricky one. But this is not a statement because it's actually a paradox, is what we would call it. Because if the statement is it's not a statement because it can't be true and it can't be false, right? If you assume that this statement is true, then the statement itself contradicts itself, right? If the statement's true, then the statement is false, right? If, on the other hand, you assume the statement is false, then the statement, that the statement is false would be true, right? So you can't assign a truth value to that statement, and therefore it's not a statement, right? Okay. Now, a simple statement contains a single idea. A compound statement contains several ideas combined together. The words used to join the ideas of a compound statement are called connectives. So statements A and C are simple statements, right? AIDS is a leading killer of women. That's just one idea. In the last 10 years, we've reduced the amount of greenhouse gas in the atmosphere by 25%. That's just one idea, right? Whereas statements B and D are compound statements, right? So B says, if you eat less and exercise more, you will lose weight. So part B has an if-then connective. They didn't write out the then, but it's saying if this, then that, right? So you have really two ideas, eat less, exercise more, lose weight, and they're being connected by an if-then connective, right? The ideas in statement D are connected by an or, right? It says Garth Brooks or Taylor Swift had the highest earnings. So if you were to write it out in full, you would say something like Garth Brooks had the highest earnings in the entertainment industry in 2015, or Taylor Swift had the highest earnings in the entertainment industry in 2015. Right? So they just kind of wrote it out in like a shorthand way. But it's two separate ideas, and they're being joined with an or connective. Okay? So let's talk about connectives then, right? So in English, we use many words to connect ideas, right? We have all kinds of conjunctions, right? And, or, like for and, let's see if I can remember them all. Fanboys, right? So for and nor, but, or, yet, so. Okay? And then we have other kinds of connectives too that are not conjunctions, like because and if then and things like that. But anyway, but in logic, we're going to boil it down to just 5 categories. So in logic, the connectives generally fall into 5 categories: negation, conjunction, disjunction, conditional, and biconditional. And so we'll take turns talking about each of those connectives so that we understand kind of how they work. All right, so let's start with negation. So negation is a statement expressing the idea that something is not true. And we represent negation symbolically with a little tilde. Okay? So for example, we're asked to negate each statement both in English and in symbols. So in part A, we're told that the statement R represents this statement, or the letter R, we'll say, represents the statement, the Retina display is included in the price of your MacBook. Now we're asked to negate this statement. So if the statement is R, then the negation would just be tilde R, right? Or we would read it not R. Okay, so we would read this not R. And in English, not R would say, Well, if R says that the Retina display is included in the price of your MacBook, then the negation is that the Retina display is not included in the price of your MacBook, right? I'm just going to say ... The Retina display is not included in the price, okay? So it's not included in the price. That's the negation. So again, we read this not R, or you could say not the Retina display is included in the price of your MacBook, right? But that's not usually how we say it in English. Usually the place where we would put the not is here after the verb, right? So we say the Retina display is not included in the price of your MacBook. Okay, same thing with part B. Give the video a pause and see if you can negate part B. Okay, I'm going to give you my solution here. So if you haven't tried it yet, again, give the video a pause, try it out. Okay, so here's my solution. So the negation, not B, is that the blue whale is not the largest living creature, right? Pretty straightforward. Okay, so that's negation. Pretty straightforward, I think. Okay, let's talk about conjunction. A conjunction expresses the idea of and we use this symbol, this little caret symbol, to represent a conjunction. There are lots of words that could express the idea of and in English, but logically they're equivalent, so we're just going to use this symbol for each of them, right? So conjunction expresses the idea of and. So let's consider the following statements. So P is the statement the tenant pays utilities, and D is the statement a $150 deposit is required. So part A here says, write the statement, it is not true that the tenant pays utilities and a $150 deposit is required, symbolically. So it asks us to write it symbolically. Okay? Well, so this first part says, it is not true that. So I have a feeling that a negation is in our midst there. Okay? But then what is it saying is not true? It's saying that what's not true is that the tenant pays utilities, that's P, and a $150 deposit is required, that's D. So notice that this part is P, and this part is D. And this and we just said, we would use this symbol here, this caret symbol, or an and. This part is a negation. So what we would write symbolically is we would say not P and D. Now I'm putting parentheses around the P and D because we want to negate this entire compound statement, right? So we don't just want to negate the P. In other words, if we had just written not P and D, that means something different, right? This means the tenant does not pay utilities and a $150 deposit is required, which isn't what we want, right? We want to say it's not true that the tenant pays utilities and a $150 deposit is required, okay? In fact, so you'll see on part B that we have a tilde on both the P and the D. So let's talk about that real quick. In fact, we might as well write out the statement in English and finish part B before we talk about this. But what would this mean? This would mean, so P is the statement that the tenant pays utilities. So not P would be the tenant does not pay utilities. D is the statement a $150 deposit is required. So not D would be the statement a $150 deposit is not required. So, and then that little caret symbol is just and. So in English, this would read the tenant does not pay utilities and a $150 deposit is not required. Okay? Now, this is not the same thing as this, right? This one says it is not the case that the tenant pays utilities and a $150 deposit is required. Now, if you're having trouble seeing how is that different from this, well, it's different because if you think about what it means for it to not be true that the tenant pays utilities and that a $150 deposit is required, this could fail if either one of these two things fails, right? So imagine that you have a situation, you're going out, you're renting an apartment, and you want to know if you have to pay utilities or if that's covered in the cost of your rent. And then you also want to know if you have to pay a $150 deposit, right? If somebody tells you, well, no, it's not true that you have to do both of those things, right? That's what this is saying. It's not true that you have to do both of those things. But that doesn't mean that you don't have to do either thing, right? It could be the case that you do have to pay utilities, but a $150 deposit is not required. In which case, saying that it's not true that the tenant has to pay utilities and a $150 deposit, that would still be valid, right? That would still be true. So, so anyway, this is not the same thing as this. If that's confusing to you, think about it, right? The thing about logic and the thing about math is that you can't just read it the way that you read a book out of a book, right? You can't read it the way that you read a story, right? You have to pause and you have to think through it, okay? And there's nothing that I can do, there's nothing that I can say to make you understand. You have to try yourself. So anyway, so if you're confused by this, pause it and think about it. But yeah, so this is the way that we would negate it. We wouldn't negate it this way, and we wouldn't negate it that way. Okay. So that's conjunction. Disjunction conveys the notion of or, and we use this little V character to represent a disjunction. So caret for and, V for or. Okay? So disjunction. Let's look at a couple examples. Right? So it says, consider the following statements. H is the statement, we will build more hybrid cars, and F is the statement, we will use more foreign oil. So H for hybrid, F for foreign. Part A says, write the statement, we will not build more hybrid cars, or we will use more foreign oil symbolically. Okay? So H, actually, go ahead and give the video a pause and see if you can do that on your own. Okay, so here's my solution. Now, H is the statement that we will build more hybrid cars. So the statement we will not build more hybrid cars, that must be not H, right? It's the negation of H. So this part of it is not H. And then we will use more foreign oil, that's statement F. And it has not been negated, it's just statement F on its own. Or gets the V symbol. So symbolically we would say this is not H or V. Okay, no parentheses, because we're not negating the entire compound statement, we're only negating H. Okay, so that's that. Now contrast that with part B. It says, write the statement not H or V in English. Okay, so again, H is we will build more hybrid cars. F is we will use more foreign oil. So H or F would say we will build more hybrid cars or we will use more foreign oil. Okay, we want to negate that. So to negate that, we could say something like, It is not the case. It is not the case that we will build more hybrid cars or we will use more foreign oil. Maybe there's a third option, right? Okay, and that's that one, right? So that's disjunction. So we've talked about, so as far as connectives are concerned, we said that we had negation, conjunction, disjunction. So we've talked about those three. And then the other two are conditionals and biconditionals. So a conditional expresses the notion of if, then. And we use an arrow to represent a conditional. Okay, so suppose that P represents the statement, the Phillies win the World Series, and C represents the statement, Carlos will win an Emmy. Okay, so let's write the statement, if Carlos does not win an Emmy, then the Phillies win the World Series, symbolically. Go ahead and give the video a pause, see if you can do that. Okay, so here's my solution. So Carlos does not win an Emmy. This statement here, Carlos does not win an Emmy. Well, we had a statement, C represents the statement, Carlos will win an Emmy. So Carlos does not win an Emmy, that must be the negation of that statement. So this must be not C. Right? And then the Phillies win the World Series. The Phillies win the World Series. That's just statement P. So this is statement P. Okay? And the if-then connective is represented with an arrow, right? So we would say, symbolically, we would say not C, arrow P. So if not C, then P. If not C, then P. Okay? Right? So if Carlos does not win an Emmy, then the Phillies win the World Series. Now the order is important here, right? If you wrote P, arrow, not C, that's not true. Well, it's not that it's not true. It's just that that's not the statement that we were meant to write out. This is a different statement than this one. This one says, if the Phillies win the World Series, then Carlos does not win an Emmy. That's not the same thing as saying, if Carlos does not win an Emmy, then the Phillies win the World Series. Those are two different statements. Okay? All right, and then part B, write the statement not P. If not P, then not C in English. Okay, so I'll give you a second to try that out on your own. Okay, here's my solution. Pause it if you haven't tried it yet. Here's my solution. So if not P, so not P. So P is the statement the Phillies win the World Series. So not P would be the statement the Phillies do not win the World Series. So, and then I'm going to have an if then. So I'm going to say if the Phillies do not win the World Series, then not C. C is the statement Carlos will win an Emmy. So not C would be the statement Carlos does not win an Emmy. Right? So if the Phillies do not win the World Series, then Carlos will not win an Emmy. Poor Carlos. Poor Phillies, I guess. Why these two things are connected, I have no idea. Maybe they're not. Maybe they're false. Maybe these are false statements, right? But anyway, this is how we would express them symbolically. Okay, the last one is one that's a little bit tricky at first. It's called the biconditional. So a biconditional represents the idea of if and only if, and its symbol is a double arrow. We're going to talk about conditionals and biconditionals a little bit more, not in the next lecture, but in the lecture after that. But basically, the phrase if and only if means that the two statements, the statements in before and after the if and only if, are equivalent statements, right? Another way to think about it is this. A, if and only if B, means both A, if A then B, and if B then A. All right? Another way to say a conditional, by the way, instead of saying if A then B, we could say A implies B. Right? In the same way here, if B then A, another way to say that is B implies A. So if A implies B and B implies A, then A and B imply each other, right? And so they're equivalent statements. All right, so that's the meaning of the biconditional, right? That A and B are equivalent statements, basically. But it expresses the idea of if and only if. So let's look at a couple examples there. It says, write each biconditional in symbolic form. The first one says, a polygon has three sides if and only if it is a triangle. Okay, so in order to write this symbolically, we need to have a way to express these statements, the simple statements within the compound statement. So I'm going to say a polygon has three sides. So for that statement, we just need a letter to represent that. You can use whatever letter you like. I might use P for polygon, right? So a polygon has three sides if and only if it is a triangle. So for that one, I might use the letter T. T for triangle. And then the if and only if is a double arrow. Right? So symbolically, we would say P if and only if T. Okay? And then part B, go ahead and give the video a pause and see if you can do part B on your own. Okay, so there are a couple ways that you could think about part B. So the first statement is pretty straightforward. The Blu-ray disc can be returned if and only if the seal is not broken. Well, we have that not in there, which means this is a negation of some other statement, right? What's it a negation of? Well, it's a negation of the statement the seal is broken, right? So if I say, so let B be the statement the seal is broken. So, in fact, actually, let me start with this first one. So the Blu-ray disc can be returned. So let R be the statement the Blu-ray disc can be returned. And then let B represent the statement the seal is broken. Okay? So then using that convention, we would say the Blu-ray disc can be returned if and only if the seal is not broken. Right? So that would be one way to express this. Now you could say, well, what if we just let B be the statement the seal is not broken? So if B just represents that statement itself, then actually let me do it this way. So if we say let N be the statement the seal is not broken, then you could write this as R if and only if n. And you wouldn't have to negate it because it already represents the statement that was given here. Okay? So this would be another perfectly fine way to write this in symbols. But I kind of like this one because since we have a not here, since we have something that says something is not true, I think it's useful to think of that as a negation of some other statement. But anyway, but they're both correct answers. Okay, part 6. It should say translate. It says translate. Translate. I'm sure I have a bunch of typos that I haven't even noticed. But anyway, translate the following statement into logical symbols. If today is not Tuesday and it is raining, then either you are hungry or it is springtime. Okay, so a lot going on here. I counted 4 simple statements that have been joined together with a bunch of connectives. Okay, so one simple statement that I see is this one right here. Today is not Tuesday, which is actually a negation of the statement that today is Tuesday. Okay, here's another one. It is raining. Here's another one. You are hungry. And then here's another one. It is springtime. So today is not Tuesday. I'm going to call that not T. All right, or I guess I should use a lowercase letter. We usually use lowercase letters for statements, so we'll say not T. Right, so T would be today is Tuesday, right? So not T is today is not Tuesday. It is raining. You are hungry. It is springtime. Now we need to join all these things together. There's a big connective here, and it's the if-then, right? Because we're saying that if these two things are both true, then one of these things is true. At least one of these things is true, right? Which tells me we're going to have basically, so and here is going to be the wedge or the caret, or is going to be this V. And then the if-then is going to be an arrow. Okay? But it's if both of these things are true, then one of these things is true, right? So that would be how we would write this symbolically, right? So we'd say not T and R implies H or S, right? If not T and R, then H or S. Okay, that would be how we write that symbolically. So we can put a whole bunch of these things together with all kinds of connectives and get really complex statements, right? But we can translate them into symbols. And this is going to be useful for us in the next section when we go to fill out truth tables, right? To help us establish the validity of various claims. So, all right. So the purpose of this lecture was to talk about statements, connectives, and quantifiers. So far we've talked about statements and connectives. So the last thing we need to do is talk about quantifiers. And this won't take us as long as the connectives did. Okay. Quantifiers tell us how many fall into 2 categories. All right. Universal quantifiers are words such as all and every that state that all objects of a certain type satisfy a given property. Existential quantifiers are words such as some, there exists, and there is at least one that state that there are one or more objects that satisfy a given property. Okay, so to give you some examples, the following statements contain universal quantifiers, right? So it says all citizens over age 18 have the right to vote. Every triangle has an interior sum angle of 180 degrees. Each NASCAR driver must register for the Daytona 500 by August 1st, right? So they're expressing that all objects of a certain type have some property. In this case, all citizens have the right to vote, right? Every triangle has an interior sum angle of 180 degrees, right? Okay. And then these three statements give us contain existential quantifiers, right? So this first one says some drivers qualify for reduced insurance rate. Okay, not all drivers do, right? But some drivers do. Some drivers qualify for reduced insurance rates. There is a number whose square is 25, right? There's a number whose square is 25. So there's at least one number whose square is 25. In fact, there are two, right? 5 and also -5. But anyway, there is a number whose square is 25. There exists a bird that cannot fly, right? There are lots of birds that can't fly, right? None of the penguins can. Okay, but anyway, but that's not true of every bird, right? It's just that there are some birds that can't fly. So universal quantifiers are saying that all of some object have a certain property. Existential quantifiers just say some of a certain object have a certain quality, right? Now, when you negate quantifiers, interesting things kind of happen. So let's look at what happens when we negate quantifiers, not qualifiers. Quantifiers. So let's look at what happens when we negate quantifiers. Okay, if we negate the statement all professional athletes are wealthy, we get not all professional athletes are wealthy. What does that mean? If we say not all professional athletes are wealthy, then what we're saying is that there are some professional athletes who are not wealthy, right? So this negation is equivalent to saying that some athletes are not wealthy. Some professional athletes are not wealthy. So what I want to do is draw what we call an Euler diagram. An Euler diagram is a lot like a Venn diagram. There are some differences that are not really important for us to consider. Like Venn diagrams have to consider all of the possibilities. Euler diagrams just consider the possibilities that we're talking about. But anyway, it's not hugely important. But let's draw an Euler diagram for this. So for the original statement, right? So for the original statement that all professional athletes are wealthy, then what you would have is something like this, right? So you would have a bubble that represents wealthy people. I'm going to call it W for wealthy. Or maybe I'll write it out. Wealthy people. And then inside that bubble of wealthy people, because there are wealthy people who are not professional athletes, right? But if all professional athletes are wealthy, then that means professional athletes all live inside of that bubble. So this is professional athletes, right? They're all wealthy. That's the original statement, right? The negation of the statement, so now for the negation, that not all professional athletes are wealthy. Well, that doesn't mean that no professional athletes are wealthy. It's just saying that not all of them are. So some of them could be wealthy and some of them maybe aren't, right? So what you would have there is these two bubbles kind of overlapping like this, so that maybe some professional athletes are wealthy, but there are some professional athletes that are not, okay? So again, this is wealthy people. Wealthy, and this is professional athletes. I'm just going to call it professional athletes. But yeah, you'll notice that these professional athletes are not wealthy, and these professional athletes are. Okay? So these ones are wealthy, or these ones are not wealthy. Okay? And these ones are wealthy, right? Right? So these ones are wealthy. Okay? But anyway, this is the negation, right? Not all professional athletes are wealthy, right? There are some professional athletes who are not wealthy. Okay? Okay. So that's kind of interesting. All right. So it's interesting because maybe I should explain my reasoning. Like, so it's interesting to me because at first glance, if you say, all x are y, and then when you think about negating that, you might think that the opposite of that is that no x are y. But that's not true, right? When we say not all professional athletes are wealthy, we're not saying that there are no wealthy professional athletes. What we're saying is that maybe some professional athletes are wealthy, but there are also some professional athletes that are not wealthy, right? So that's actually what we're saying. So our universal quantifier becomes an existential one, okay? All right. And then let's look at another example. If we negate the statement, some students will get a scholarship, we get, it is false that some students will get a scholarship. But what does that mean? How would we usually say that in English? Right? Some students will get a scholarship. If we negate that, we say it is false that some students will get a scholarship. Well, if we negate that, if it's false that some students get a scholarship, then it must be the case that no students get a scholarship, right? If there's not even one student who gets a scholarship, then no students get a scholarship, right? So this negation is equivalent to saying that no students get a scholarship. So again, let's draw an Euler diagram for the original and for its negation. So for the original, so some students will get a scholarship. We might have this situation, right? So this bubble will represent maybe students. And this bubble will maybe represent students who get a scholarship. Oh, no. How would we do this Euler diagram? Because if you're going to get a scholarship, you've got to be a student, right? So if you're a student, if you're getting a scholarship, you got to live inside of that student bubble, right? Let me think about this. Well, the book has it this way. I'm going to go with what the book's saying. Scholarship. I guess you could get a scholarship without being a student. I don't know. Maybe this is a bad example. But anyway, so this is what the original statement would say, right? That some students get a scholarship, right? So these are the students, right? Some students get a scholarship. Okay? Now here's the negation. So we said it is false that some students will get a scholarship. So the negation is equivalent to saying that no students will get a scholarship. Okay, so then that means that you've got a bubble here representing students, and then you've got a bubble here representing scholarship. And there's no overlap between the two because no students get a scholarship, right? So this is the negation. All right, so to summarize this, right, if we negate all, we get, that's the same thing as saying at least one is not. So saying not all are blank is the same thing as saying at least one is not blank, right? So just like the wealthy athletes, not all athletes are wealthy. That means at least one athlete is not wealthy, okay? And then if we negate an existential quantifier, so if we say not some are blank, right? So so it is false that some students get a scholarship. That's the same thing as saying none are blank, right? So that's the same thing as saying no students get a scholarship. Okay, so the negation of all is at least one is not. The negation of some is none. All right. So let's negate each quantified statement, last couple of examples, and write it in English. Okay, So part A says all customers will get a free dessert. All customers will get a free dessert. So the negation is not all customers will get a free dessert. So we could write that as like not all customers will get a free dessert. But that's equivalent to saying at least one customer will not get a free dessert. Right? So these are both good ways to say it. The second way is maybe a little bit more clear, right? At least one customer will not get a free dessert. Okay. Part B. Some tablet computers have a 2-year warranty. So we want to negate this. So to negate it, kind of originally, we would say it is not the case. It is not the case that some tablet computers have a 2-year warranty. Okay? It's not true. That's not true. Well, if that's not true, right? If it's not true that some tablet computers have a 2-year warranty, well, that must mean that no tablet computers have a 2-year warranty. So no tablet computers have a 2-year warranty. Okay, and that's probably a more clear way of saying that negation. And that will do it for this section. So we'll talk more about this in the future.